Okay, so it looks like we are live on YouTube. Thank you very much to those of you watching this live. As I think you have gathered, this is the last couple of episodes. This is a bit of a test for us, transitioning from a radio-only podcast to a blend of radio and also video, mostly on this YouTube platform. So I appreciate your patience as we work out all the wrinkles in that. I'm especially grateful to Professor Brian Fields for being our guest today. Thanks so much for joining us here at the Star Spot.
Oh, thanks. I'm excited to be here.
Well, we're going to talk about a really fascinating topic because it combines history and fairly ancient history of our planet with astronomy and astrophysics. And we're talking about the connection between astrophysical events, in particular supernovae, and extinction and mass extinction events here on Earth. So it's a really interesting confluence of different areas of scholarship. First of all, why don't I just get right into it and ask you, there's a particular event that your team has been studying, a particular event here on Earth. Can you tell us more about that event? When did it happen, and why was it significant to Earth's history?
Yeah, great. So we're interested, just as you said, in the connection between cosmic events, cosmic explosions, and their potential effect on life on Earth. And to sort of set the context, so life on Earth has existed for billions of years, and has grown and complexified over time. But as you probably know, it occasionally is punctuated by these drastic die-offs, where many species die all at once, this mass extinctions. And the most recent, and not the worst, was 65 million years ago when the dinosaurs died. And that actually was something astronomical. It was an asteroid that fell on the Earth. But it turns out there are 4 other sort of major mass extinctions. And we're interested in one of the earlier ones called the Devonian, the end of the Devonian geological period, which was about 360 million years ago. And it's long been known that that's the time when there was an extinction, but it's a little different from the dinosaurs because when the dinosaurs died, they all died abruptly. At the end of the Devonian, that was a period that stretched 60 million years. At the very end of it, maybe 10 million years, there was a gradual sort of loss of biodiversity, meaning there's species born, species die, but not as many new species were formed as old ones would die off. So there was a gradual die-off. That's not due to a supernova. That's probably due to other things. But right at the end, there were a couple of very punctuated die-offs of species. And the very last one, called the Hengenberg event, my dog is excited about it, marked the end of the Devonian period.
So as you say, the Devonian was a complex era, and there was a lot going on, culminating in this extinction event. Do you propose, therefore, that there were a few causes of the gradual die-off, and then that final more mass extinction event? So in addition to the supernovae at the end of it, were there other probable things going on, and were those a combination of terrestrial and extraterrestrial causes?
Right. So we think, so overall, there probably were multiple causes, and they look different in the record. There's a slow die-off and then 2 really punctuated events, at least 2 really punctuated events. To set the context, the end of the Devonian is an interesting period. It's the first time there was really life on land. It was the age of fishes. Fishes really became abundant throughout the oceans. And the Earth was, it wasn't quite Pangea, when all the continents fit together like a jigsaw puzzle, but it was almost there. And so it was a very different landscape. And the thinking is, as Pangea started to happen, the ocean was just this one big giant uninterrupted thing, and it was harder for species to find niches to develop in, in a sheltered kind of way. And so the thinking is, I'm told by paleontologists, that's responsible for the gradual die-off, but it hasn't been cleared what these punctuated events were for. And that's where we came in, following a recent paper where an English group out of Southampton showed that this final event at the end of the Devonian was marked with a drastic loss of ozone from
Right.
the Earth's stratosphere. And they considered a couple of causes, but we came in to point out that for decades now, people have pointed out that astrophysical explosions in space, can severely damage the Earth's ozone. And that was the starting point of our study.
Now, how significant was this particular end Devonian extinction event compared to the others? You mentioned the one with the dinosaurs being actually a more modest extinction event, but there have been, I think you said 4 or 5 in total,
Right,
so-called
right,
mass extinction events. Where does this one sort of fall in that larger context?
right. So the overall in Devonian is sort of comparable to the others, but not the biggest one. The Permian is the biggest one. That was really we almost all lost it then. Um, and and again, it's a combination of things. It's complicated. There's a gradual die off, but then some severe punctuated events, which aren't by themselves as severe even as the dinosaurs, but they're still quite dramatic. And it's those that we're trying to explain.
Perfect. So that's great. With that background, why don't we jump into what your team has proposed as an explanation again for that ozone depletion phenomenon?
Yeah. So there's recent evidence. I was looking at these old. It's amazing how geologists do this. Looking at fossil spores, plant spores, and they were all mutilated and they look kind of burnt, and that's what you get if they're exposed to harsh ultraviolet radiation from the sun. Um, and so and so what we pointed out is that explosions in space can do this, and any number of kinds of astronomical events can actually cause this, including just eruptions in the sun. There are these solar flares that happen occasionally, and once in a while, if you have very, very large ones, they could be quite damaging. But we're able to rule out almost everything by looking at the geological record, because this last die-off of species, this Hangenberg event at the end of the Devonian, lasted for many thousands of years. But many explosions in space, including eruptions on the sun, is one and done. They zap the Earth, they irradiate the atmosphere, the outer atmosphere of the Earth, the stratosphere, and strip off the ozone layer. And then that's a damaging thing, a grievous thing, but the ozone recovers in about a decade. So that wouldn't lead to species dying off for thousands of years. And there's only one kind of astronomical explosion that removes ozone but can keep it away for a long time, and that's a supernova explosion.
Did your team compare those astronomical explanations with terrestrial ones? I know volcanism, for example, is often invoked as an explanation for potentially some of the other extinction events, whether mass or otherwise. But is that a possibility in this case?
Yeah, absolutely. And in fact, the discoverers of this ozone depletion, they considered volcanism themselves, and they were already able to rule it out by not finding some of the chemical traces, mercury, I believe, and some other chemical traces that you would expect to see if there was increased volcanism, which in other mass extinctions absolutely does seem to play a role. So it's absolutely the right thing to look for. And in fact, so ruling that out, they said that there's some evidence that during part of this time there was a period of global warming, and they were arguing that that global warming, putting more water vapor into in the atmosphere, ultimately could lead to ozone destruction. And of course, if that really is an effective mechanism, that has consequences for today and us. So that's something we certainly care about and needs more follow-up. But whether that would work over this long extended period of time is not so clear. And so we're proposing an alternate explanation, but really both of them need to be pursued. So it's early days. This is a new discovery of this ozone loss, and we're all trying to come up with different explanations.
So in terms of determining which one might be the correct explanation, what would some of the evidence look like, and what is there a plan to go kind of hunting for that
very
evidence?
Good.
Yeah,
very good. So right. So and I can tell. So that's exactly what our paper was about. Is suggesting how supernovae can remove the ozone, and then how we can test consequences of that. So maybe to say a little bit more of what the supernovae do so we can appreciate how we go looking for them. So, so the supernova damage is sort of a double whammy. It hits you twice. So the supernova explosion itself, this incredibly energetic event, will be very bright. To the naked eye, it would be very bright. This would be an event that would be brighter than the full moon at its brightest, at the kind of distances we're talking about, and would persist for in the sky for more than a year. And at its brightest, if you were up during the day, you would see it during the day. And at night, it would be brighter than the full moon, so you could read by it. So it'd be really impressive. Um, but in addition to that visible light that we would see, the supernova also emits much more dangerous photons, high energy light in the form of ultraviolet rays, X-rays, and gamma rays. And those are the things that can strip off the ozone layer. And then they're gone after about a year. And then in 10 years, the ozone recovers. So the Earth kind of tries to get on with life again. But the supernova blast flings out most of the mass of the star. We're talking about a massive star, 10 times the mass of the sun, exploding, and most of the material of the star is flung out into space at a few percent of the speed of light. That stuff sweeps up interstellar matter and eventually overwhelms and sweeps over the solar system. And when it arrives, that blast from the supernova is a particle accelerator. We see this all the time. Supernovae accelerate high energy particles, and those particles irradiate the Earth again and once again remove the ozone layer, but now they keep it off for thousands of years. And that's how we can get an extended period of ozone loss.
Got it. Got it. And that's how it differs from some of the other explanations.
That's exactly right. And then that has consequences for testing how this works. That has consequences because this loss of ozone also comes with these high energy particles, these cosmic rays. They have other consequences that one is, it turns out cosmic rays are the sort of, are found to be the seeds for lightning bolts. The high energy particles go through the atmosphere, create ions, and those form pathways for lightning. So this could have actually increased lightning strikes. That could have been global fires. That's something you can look for in the record. And the cosmic rays also affect the atmospheric chemistry. So there's some chance that this could ultimately lead to cloud formation and some global cooling effects, which could be searched for. And there's some evidence for that. But another thing is the die-off of the species of themselves. These high-energy cosmic rays create very penetrating particles called muons, which go deep into the Earth. So not only is there a loss of ozone, so we would put on our hats or our sunblock, but if you're a phytoplankton, there's nothing you can do about that. But even if you go under the ground or into the oceans to escape the ozone, these high-energy muons go down half a mile. And so they would be particularly damaging for big critters, megafauna they're called, which then just be susceptible to a lot of hits from these. So the pattern of extinctions is also a prediction. But the most fun thing is something that would be very hard to find, but it would be the absolute smoking gun. And that is to find debris from the supernova, literally, that is rained upon the Earth. So the thing to appreciate is supernova explosions, like all stars, are ultimately powered by nuclear fusion. It's in the extraordinarily hot, dense interior of stars, and particularly supernova explosions, there's a blizzard of nuclear reactions. And in fact, supernova explosions make most of the elements that we are made of. We are the children of supernova explosions. But that's great if you're far away, but if you get too close, it's not so good. And in that blizzard of reactions, many of the elements we're made of are formed, but also some unstable radioactive nuclei are made. And that's what we're particularly interested in, because they make a great signature of the supernova once they're brought to the Earth and rain down upon us, because they're sort of like green bananas. So everybody understands green bananas. Well, bananas sort of ripen and then rot over time. And if you find a green banana in Toronto or even in Illinois, you know, first of all, it was made recently. And it wasn't made here. Something brought it here. Well, it's the same with these radioactive species from supernovae. They're radioactive, meaning they're unstable nuclei that want to decay to something that's stable after a certain amount of time. And so if you find them before they decayed, that's like green bananas. So you know they were made recently, but also the Earth doesn't make them, so they had to be brought here. And so there's a couple of different kinds of radioactivity, plutonium and another species called samarium. And we're not sure if the supernovae make these, but if it was so kind to do that, that would be the smoking gun to find these tiny traces of radioactivity in the Devonian fossils.
So the actual material brought to Earth by the supernova itself, left behind as a telltale fingerprint of these events, of the
Absolutely.
event. And with the asteroid that would have caused the extinction event, we're familiar with when the dinosaurs went under, we have been able to find basically the remnants of that asteroid material.
Exactly. It's very similar to that.
Precedent there. Yeah.
It's very similar to that. And the asteroid actually delivered more material to the Earth, so it's easier to find because the whole thing fell on the Earth. And so there's this layer of material that's enriched in rare elements that are more abundant in asteroids, like iridium famously. So we have a very similar idea, but here the amount of material, supernova is so far away that the amount of material is much, much less. So there won't be some kind of visible layer. It'll take very sophisticated techniques to identify the small amount of radioactivity. But then if we're able to find it, not only does it tell us that that supernovae are part of the history of life on Earth, but as you already were implying, it allows us to learn something about the nuclear fires in the cores of stars and learn more about what kind of star exploded and what was going on in these nuclear reactions during the explosion.
Learn more about stars light years away from material we might find here on our own planet. That's pretty mind-boggling.
Right.
Now, so that's studying the Earth and looking for those signs here. Is there any possibility after over 360 million years that we could actually find remnants in the galaxy of this, what was a star is now long dead, but maybe there's something still there 360 million years, everything's moving around the galactic core. I don't know if it's even going to be anywhere near where it was 360 million years ago. But is that a search that has any kind of legitimacy?
That is a great question, and you framed it exactly correctly. So 360. The problem is the short answer is no, because it's too long ago. When supernovae explode, they make these gorgeous remnants, and you see an image above my head of one of those if you're on video. That's in X-rays from 300 years ago, and they're gorgeous. But after at most a million years, they kind of fade away and mix in with the rest of interstellar material. So this thing is long gone, not to mention, as you say, we and all the stars around us in our Milky Way are going around the center of the Milky Way, and we've gone around almost twice since this explosion happened, and everything's been well scrambled since then. But it's a good idea. This general principle still works. It turns out that we know that it's not crazy to think supernovae make radioactivity. I can't help but mention, since you brought all this up, that we have very good evidence that there was a more distant supernova about 3 million years ago, because we have found a different kind of, an easier to find kind of radioactivity at the bottom of the ocean and on the moon and in Antarctic ice from a supernova 3 million years ago, and we're still living in the bubble from that supernova. So it's not crazy to imagine this sort of thing can happen. But that was further away. That was a near miss. But we're talking about a direct hit much longer ago.
No, I'm glad you brought that up, because I wanted to explore that. Now that we've sort of introduced the concept of supernovae being responsible for extinction events, I was going to ask you, are there other examples where there's a candidate explanation is a supernovae, and you've just given one. I guess would that be the most recent event? I mean, it's only 3 million years ago.
Right. So this is very recent. This is 3 million years ago, and we literally find that by looking. There's sediments at the bottom of the ocean that pile up like tree rings, and you can find there's a layer that has supernova material, and it's radioactive. It's green bananas. This is a different kind of radioactivity. It only lives for a few million years, so it wouldn't work for the Devonian. So that's why we're not looking. It's a radioactive form of iron that won't work for the Devonian, but definitely shows there was a nearby supernova at least one 3 million years ago. And that certainly didn't cause a mass extinction because we're talking about it. 3 million years ago, if it caused a mass extinction, we wouldn't be talking about it. But although there's ongoing work about whether there was some less catastrophic damage to the biosphere. But it's a nice demonstration that this kind of thing really can occur. But going back to the Devonian, I should mention, in terms of other mass extinction, remember the Devonian, there was this gradual loss of life, probably due to the formation of Pangea, but then there were these punctuated events. This ozone loss has been found for the last of these punctuated events, but there were earlier ones. And the thing to appreciate is supernovae, the explosions of massive stars, tend to come in bunches. So massive stars are social. They hang out with other massive stars. And they typically are born in pairs. So essentially all massive stars are in binary systems where there's at least two of them together, and generally with another massive star. And so when one explodes, it's very likely that that another one is going to explode soon in astronomical terms, meaning within 1 million years. So it is entirely possible that some of these earlier abrupt extinction events at the end Devonian could have been from siblings of the supernova that led to the ozone loss we've been studying.
Wow, that's fascinating. And then beyond those examples, are any of the other extinction events we're aware of, or has a supernovae been implicated or suggested in any other case, or are we just kind of now looking at that possibility?
So well, with supernovae, we're just now looking at the possibility, but I would be remiss to mention that some of my co-authors on this paper, the group at Kansas, Adrian Malott and Brian Thomas, have proposed that a different extinction, when it's still one of these major mass extinctions called the Ordovician, which is a little after the Devonian, that the pattern of die-off there is consistent with not a supernova, but a related cosmic explosion you also wouldn't want to be very close to, called a gamma ray burst. And these things there's a couple of ways to make them. Either a massive star can do this, but also two merging neutron stars, and it creates this this beam, like a giant laser beam of gamma rays, which can reach out much further than the damaging bits of a supernova. And so the pattern of extinctions at the end of the Ordovician might be due to, are consistent with being due to a gamma ray burst, and there's ongoing work on that.
The kill zone is larger, but I think it's a more kind of directed burst, right?
So absolutely right. So it has to be pointed at you, to be a problem. If the bullet's not pointing at you, not a problem. But if it is, it's very bad. Yeah.
Well, this is actually where I wanted to go, and it'll be sort of the last set of questions that I have for you, and that is in terms of how much danger these things pose. I think one way to understand that is the kill zone itself. But then I realize not all supernovae, pack the same punch. So some are more sort of powerful or explosive than others. Is that not the case? Would that not be factored into
so gamma ray bursts and supernova are definitely very different because the gamma ray bursts are beamed. So the dangerous radiation comes out in a tight beam. So bad if you're in the beam, fine if you're not in the beam. Supernovae they're not completely spherical, but they're much more spherical. So they send out their dangerous ionizing radiation, ultraviolet, gamma rays, X-rays, in all directions. So their blasts are very similar, and those are the things that are the most dangerous. So as far as we can tell, supernovae are all about the same amount of dangerous. Some are a little more powerful than others, but they're all pretty dangerous. But that reminds me of something I would be remiss if I did not say. 2020 is a miserable year already. Let me be absolutely clear. I'm not trying to make 2020 any worse. Of all the many things we need to be worried about right now, a nearby supernova is not one of them. It is not a present danger. Because as you say, this kill zone, this kill distance, we call it, is, well, for the Devonian, we're talking about something that's about 65 light years away, 20 parsecs for the experts out there. And that is extremely close in astronomical terms. That's our very nearby neighborhood. Our galaxy is way bigger than that. This is a very nearby neighborhood. And if we had any massive star so close, they're enormously luminous stars. It would be by far the brightest star in the sky. They can't hide. And we know there's nothing remotely so close. Something like Betelgeuse, which will explode someday, it'll be fantastic. That's much further away. That will be fun fireworks to watch, but nothing dangerous. And there's nothing at all in the kill region today. So there are many things to worry about in 2020, but this is not one of them.
Not for 2020, but I think it's worth emphasizing it, and maybe a good way to sort of conclude the discussion, just to what extent we're learning how much our Earth is intricately part of this larger galaxy and even universe, and we're affected by these events, whether they're supernovae or asteroid collisions or gamma ray bursts, perhaps. That and you made the point earlier that in fact we're made of the stuff of supernovae. In that case, probably from billions of years ago, but there's a factor there that we can't lose sight of. I guess there's almost a philosophical kind of takeaway from that, perhaps.
I couldn't agree more. I couldn't say it better, but I'll try. Because I couldn't agree more. That to me is one of the most interesting things about this, that we owe our lives to the cosmos that formed the very elements we're made of, created the conditions for the solar system and the Earth to form. And supernovae were essential to that. But the cosmos giveth and the cosmos taketh away. And so an overarching message here is that life on Earth, just as you say, life on Earth does not exist in isolation. We are citizens, not just of our little town or even country or the Earth, we're citizens of the cosmos. And the cosmos intervenes in our lives. Often, mostly imperceptibly, but sometimes, every long while, the cosmos can intervene ferociously.
Well, thank you for putting things into perspective, an astronomical perspective. It's been a real pleasure discussing this fascinating topic with you, Professor Brian Fields. I'd love to have you back on as we hunt for the smoking gun, and hopefully we find it and we bring some finality, I guess, to this debate. But again, really appreciate you joining us on the show.
Thank you very much, and thanks for your patience with my dog.
I have a cat, and he's about as loud as a dog, so I'm used to that sort of intrusion. Not a problem. Well, thanks again, and we'll get the episode out to you just as soon as it's available.
Thanks very much.
Take care. Bye now.